Hello, my name is Kate Smith, and I'm here today with my coworkers Derek Wilson and David Pless. All three of us are program managers at Microsoft working in the Intelligent Query Processing, or IQP space. Today, we will be presenting a deep dive into Intelligent Query Processing for SQL Server 2022. I'm going to start by giving an overview of how the Intelligent Query Processing space has grown over time. The boxes shown here in light blue are the features in Intelligent Query Processing that were released with SQL Server 2017. In SQL Server 2019, we added a number of new features shown here in the white boxes. And in SQL Server 22, what you're going to hear about today are the additions that we made for SQL Server 2022, including cardinality estimation feedback, DOP feedback, 2 improvements to the existing memory grant feedback work, which include percentile grant feedback and feedback persistence. We are also going to talk about parameter-sensitive plan optimization and optimized plan forcing. Before we go into the details about all of these features, my colleague David Pless will be talking about Query Store on by default and Query Store hints.
So of course we love Query Store. Introduced in SQL Server 2016 and on by default in Azure SQL Database, Query Store greatly simplifies the overall performance tuning customer experience by capturing queries, execution plans, and associated runtime statistics. So you definitely should be leveraging Query Store for all its benefits of being a flight recorder for SQL Server. And as we may know, Query Store also helps database administrators force plans when needed. Now, in SQL Server 2022, what is important to understand is Query Store's ability to record query history along with the query text, the query plan, and other metadata is being leveraged in new and exciting ways to unlock new capabilities. So fundamentally, Query Store is a foundational component for Query Store hints and many of the new IQP features. So let's first talk about Query Store on by default. Let's talk about Query Store on by default. So one of the first concerns we may logically have is the overhead of having this on for all user databases. Is this going to be an issue? So the first thing to know is that we capture plans, query text, and performance data all asynchronously. Secondarily, Query Store on by default has been the standard for Azure SQL databases for a long time in the form of query performance insights. So if you connect Management Studio to an Azure SQL Server, Azure SQL database, you're still using Query Store capabilities underneath, but we just call it Query Performance Insight in the Azure SQL Database blade. So the bottom line is we've been using Query Store on by default for years in the cloud, and we've also improved its scalability with customer feedback and valuable insights. So starting with SQL Server 2019, we now have better defaults as the capture mode has been changed from all to auto, and the max size has been changed from 100 megabytes to a gig. And with auto, we started capturing the query details when we hit any of the following thresholds: 1 second for a compile, 100 milliseconds for the execution CPU time, and 30 executions for the execution count. We also improved ad hoc workloads with Query Store, and with several cumulative updates in SQL Server 2019, greatly reduced the overhead of leveraging Query Store, as Query Store now imposes internal limits to the amount of memory it can use, and will automatically change the operating mode to read-only until enough memory has been returned to the database engine. So all of this helps prevent performance issues in SQL Server. And additionally, if needed, custom capture policies can help further tune your capture through Query Store. Custom capture policies are already available to help fine-tune your capture if you're looking to reduce overhead. For example, if you have an environment with heavy ad hoc workloads that cause higher Query Store overhead because there's a higher cost to capture query details, you can use custom capture policies to be more selective about which queries you're trying to capture. You may choose to only pick the most expensive ones, for example, to help make sure Query Store captures the most important, this could be repeated or expensive queries in your workload. So why would you need to do this? If you're having a very intensive ad hoc workload driving long compile times and causing Query Store bloat, then you might want to use a custom policy. However, most of this is solved with the self-throttling we have in SQL Server 2022, so you can expect much less queuing, and we have additional failsafe as Query Store will go into read-only mode for a while until it catches up. So you can see here on the screen an example of a custom capture policy. What are query hints? So before we jump into Query Store hints, we should probably talk about query hints, as there are times that we do need to influence query plan behavior. So many of us are already leveraging query hints in our code to influence behavior. Query hints are specified via the option clause, and while query hints help provide a solution to performance issues, they do require changing the query text, changing code. But why change the query plan behavior? Why interfere with the optimization process? Ideally, the query optimizer will select an optimal execution plan for a query. That's what it's designed to do. But this doesn't always happen. And when it doesn't happen, a database administrator may need to optimize for a specific condition. Otherwise, we get stuck with a bad plan, and a bad plan will lead to bad performance. We may have a stored procedure, for example, where the cardinality of the select can vary wildly, causing you to need to use a recompile hint. You may need to put a limit on the memory grant size for a bulk insert operation. You could need to limit the maximum degree of parallelism or a report that runs on the same system as your critical OLTP environment. Or you may even need to lower the compatibility level for a particular query to prevent having to lower the compatibility level at the database scope, because you realize other benefits at being at that higher database compatibility level. So there's many reasons you may need to influence plan behavior. An example shown here, we're disallowing batch mode and also telling SQL Server to recompile the query on each execution. So as discussed, there are many reasons to leverage query hints. They do require making changes to your code, making changes to the queries. And this is usually something that cannot be done without the application owner or vendor support. So DBAs may not always be able to make these changes directly to T-SQL code. For production environments, this is definitely a struggle, but also for vendor-based solutions, as the T-SQL may be hard-coded or automatically generated by the application. So what was our previous options? Well, previously, DBAs had to rely on plan guides, but they were very difficult to use. So what are query store hints? In short, Query Store Hints provides a direct method for developers and database administrators to shape query plans without changing your application code. Query Store Hints is a new feature that extends the power of Query Store. But this does mean that Query Store Hints requires that Query Store feature be enabled and that your query and your query plan is captured by the Query Store. So just like plan guides, Query Store hints are persisted and will survive restarts, but Query Store hints are much easier to use than plan guides. And Query Store hints will override other hard-coded statement level hints and plan guides. Queries will always execute as opposing Query Store hints will be ignored. For example, one thing to know is that the recompile hint is not compatible with force parameterization set at the database level, but this does not cause the query to fail. If the database has force parameterization set and the recompile hint is part of the hint string set in Query Store for a query, SQL Server will ignore the recompile hint and will apply any other hints as they are leveraged. So how do you use query store hints? The workflow for query store hints is pretty straightforward. First, the query is executed. Then the query plan and the execution details are captured into the query store. Then the database administrator creates a query store hint on a query. Thereafter, the query is executed using the query store hint. Now, the DBA's part is very important to drill into. Okay, so to use query store hints, this is what the DBA will do. They'll identify the query store query ID of the query statement that the database administrator needs to modify. And they can do this in a few ways. So they can find this query using the query store catalog views. They could use SQL Server Management Studio built-in query store reports. Or if it's in Azure SQL, use the Azure Portal Query Performance Insight for Azure SQL Database. Once a query's been identified, they will use the SP query store set hints with the query ID and the query hint string that the database administrator wishes to apply to the query. This string can contain one or more query hints, as can be seen in the example. Again, query store hints overrides hard-coded statement level hints and existing plan guide hints. If a query hint contradicts what is possible for query optimization, the hint will not block query store execution and the hint will not be applied. In cases where a hint would cause a query to fail, the hint is ignored and the latest failure details can be viewed in the SYS Query Store Hints Dynamic Management View. Okay, back to you, Kate.
Thank you, David. Now that we understand more about how the query store has changed and is different in SQL 2022, specifically regarding query store hints, let's talk about 3 feedback features, one of which uses query store hints explicitly, and the other 2 use query store in a way that is similar to how query store hints works, but without exposing the feedback as a query store hint. So these 3 features are memory grant feedback, degree of parallelism feedback, and CE or cardinality estimation feedback. The workflow for all 3 of these feedback mechanisms is basically all the same. The user executes a query. Then the system looks at the query, looks at its performance, CPU consumption, parallelism, various factors, then decides, does this query qualify for feedback? If we think it might and might benefit from some feedback, we suggest those changes to the system. When those changes are suggested, we then try the next execution. We use those suggestions to see if they actually improve query performance. If so, then we can verify those changes and persist them. So let's look at this in detail with cardinality estimation feedback. So what is cardinality estimation, or CE? There's a lot of this talk about the model. What is the model? It is a set of assumptions that we use to interpret statistics and make estimates as we combine expressions within the query tree. So we need to sort of have a set of assumptions that we can use because that is the framework with which we interact with any statistical data that we've already received. There historically has been one model for CE. It hasn't always been that same model, but the challenge that cardinality estimation hits is that inside a workload, some queries will work better with one model and some queries will work better with a different one. So CE feedback allows us to tweak and modify the model used on a per query basis and in a do no harm way. Let's look in detail. So CE feedback starts with this default model assumption. We have to start with the basics that we have that all queries get today. Then, after we observe the query and how it executes and the kind of results we get, We then maybe modify the assumption. We then run with that assumption and validate it to see if the assumption is better. If it's better, we incorporate it into the query for future executions. If not, we don't use it. Let's start with model assumption number 1, uniformity. Uniformity basically means that we look at data within a histogram bucket or step and assume that within that step, the data is uniformly distributed at an average rate for that bucket. So we use it when interpreting data from on-disk histograms. This extrapolates into when we do sort of a row goal query. So if you have a query that asks for the top n or the fast n, that type of thing, what can happen is we could say, well, we think that there are this many rows in the table that qualify, and once we think that, we could say that's a lot of them. So we could just scan a few pages and we should get enough rows to meet this goal. But if the data is not distributed uniformly, we end up scanning a lot more pages than we set out to scan, which becomes inefficient. So CE feedback can disable that row goal and enable a seek on the table. Let's do a demonstration now of cardinality estimation feedback row goal. Welcome to the SQL 2022 row goal demo. As you can see, I'm using SQL Server 2022, and I have an instance of an AdventureWorks database installed. We'll do a few things to configure the query store, set up the database, make sure our procedure cache is clear, those sorts of things to get a clean demo. Then we'll set up an X event session to monitor and capture cardinality estimation feedback related X events. Once we start that, we'll open a window to allow us to watch the data as it comes in live. As we are doing the demonstration, we hope to see X events show up. Now we have a query that selects the top 1,500 sales order IDs from sales order header joined with sales order detail on a particular date. We can run that query a number of times. That signals to CE feedback that perhaps this is a frequently executed query and we should see if we can make it better. We can flush to the query store and then we can query the query plan from the query store. And you can see here we're doing a scan of both sales order header and sales order detail. However, the actual number of rows is much greater than the estimated number of rows returned for this query. At the end of this execution, we hope to see that cardinality estimation has kicked in, and we think that we might be able to disable optimizer row goal, and that might make the query run more quickly. On this next execution, we will try that and see if it is indeed valid. We get a validation X event that shows the new CPU time versus the old CPU time. So it looks like by disabling optimizer row goal, the query has executed more quickly. We can also look at the execution plan. And you can see our estimate from before was too low. Our estimate is now higher, but more accurate. So now we will stop the X event session, but we can look in the query store hints table, and you can see, in fact, we have added disable optimizer row goal to our query hints for our query, and that the source of that is CE feedback. We can also look at query store plan feedback and see that we have indeed created some feedback using CE feedback that we should disable row goal and that the verification has passed. That is optimizer CE feedback row goal optimization in action. Now, model assumption number 2, independence or not. When you have multiple predicates in a query, so something like column equals constant and other column equals second constant, that type of thing. We talk about the selectivity of that predicate, which means the number of rows out of the total number of rows in the table that qualify for that predicate. That's the selectivity or probability of the predicate. When we assume that these predicates are independent, we just multiply those selectivities together. But in most cases, predicates are not actually fully independent. There's a reason that we're querying for these two data points together. And so we can actually assume sometimes that they're completely correlated. So everything that is in Seattle is also in Washington. But sometimes they're not completely correlated. There's some connection, but it's not a total overlap one way or the other, but they're not totally independent. So what do we do for CE feedback? We start at this sort of partial correlation measure. We call that exponential backoff. Now, it's been talked about and published before, so we'll just drop that name there in case you want to do further research. It starts there at that partial correlation, and then it looks at how the query is actually executing and decides, do we need to go more towards independence or do we need to go more towards correlation? If our partial correlation estimate is too high, then we can assume that there's more independence. And if it's too low, we would assume more correlation. So let's look at a demonstration of CE feedback correlation. Welcome to the SQL 2022 Cardinality Estimation Correlation Do No Harm demonstration. As you can see, I'm using SQL Server 2022 and a copy of the AdventureWorks database. First, we're going to set up our environment. That would be to configure our compatibility level and configure query store. Next, we make sure that we've cleaned the procedure cache and other things to ensure a clean, smooth demo. Next, we will set up X-event capture by creating an X-event session to monitor cardinality estimation related X-events. Afterwards, we will alter the event session to start it. At this time, we can choose to watch the data live in a separate window as we do our execution. Now we have a query that selects from addresses. You can see that we've got two predicates, one on an equality predicate on state or province, and an equality predicate on city. They are used in a conjunctive clause. If we assume independence, then we would multiply these selectivities. If we assume partial independence, we would multiply these selectivities with a limiting factor. And if we assume correlation, we would choose only the most selective of these three predicates. We always start with that middle option, sort of partial correlation option. After we've run the query a number of times, cardinality estimation feedback wakes up and says, well, maybe this query is run frequently enough that we should do some analysis on it. Before we get there, let's have a look at the query plan. The query plan is very simple, but you can see that our actual number of rows and our estimated number of rows are different. We have underestimated the number of rows, indicating that the correlation model we're using is too selective and underestimates the number of rows. So after we do this execution of the query, we should see an analysis event show up. This event would basically say, this is what we think we should try. Assume min selectivity. That is the correlation model. We assume the selectivity of the conjunction of the predicate is equivalent to the minimum selectivity of the minimum selectivity predicate, just one of them, instead of computing the conjunction. Now we do a validation step. Before we go there, let's have a look and see how our estimates are now. It looks as if our estimates are exactly on point. So how did we perform when we do our validation? If we look closely at this, you can see that the plan hash did not change. As a consequence, we, by design, choose to emit a CPU time of 0, indicating that when cardinality estimation feedback changes are in effect, but we do not change the plan, we do not want to keep that feedback in place. So the CPU time may or may not have gotten better. We know that the estimate did get better. But since the plan didn't change, we don't feel that this is a query hint that we should keep. So as we continue to run this, we will discard that hint and go back to our misestimate, but that same original plan, which was good enough. Now, let's stop the X-event session and have a look in query store hints. Do we see a hint for this query? And indeed we do not, because we chose to do no harm, because the plan didn't change, and we did not keep this as a hint. But we can look in the query store plan feedback table, and here you can see that we had CE feedback that was tried, and that the verification regressed. So we chose not to keep this plan feedback, and instead go back to the original plan without feedback. And so that is do no harm correlation in SQL Server 2022. The third model assumption to talk about is containment. The basic idea is that users query for data that exists. So, for example, when we're probing histograms where we have an equality predicate, we assume that something is going to match that equality predicate from within the histogram, even if it's not actually there. Remember, our histograms are just statistical abstractions of the data and don't have every data point represented. But we can also use containment in joins. That has to do with the assumption we make about how the data lines up and matches from the two incoming relations into the join. And there's two approaches. Simple containment, basically, the idea is that it assumes the join predicates are fully correlated. So after you've done your filtering, then we assume the filtering selects the values that are going to join and that they do join. Base containment assumes a relationship between the tables themselves, but not a relationship after the filters have been applied. So we estimate the join based on the base table properties, and then any filters that are on top of those tables we use to scale up or down our estimate appropriately. Let's look at an example. So here we have a join between sales and returns. The join is an equality join on receipt number. There's a filter on sales for toys and a filter on returns for a specific date. Base containment assumes that there is a relationship on receipt number between returns and sales, that everything that you've returned in terms of receipts, every receipt that is processed for return has been sold. That makes a lot of sense. So then we would assume that there's a match there and a containment assumption between returns and sales, and then we apply filters based on the selectivity of the respective filters, toy and date. Simple containment estimates those filters first and then assumes a complete match. In this example, which is a bit pathological for simple containment, it doesn't make any sense. It assumes that everything returned on January 1st, 2013 was a toy. But we all can think of examples when the filters used into a join relationship actually do create a containment relationship once the join occurs. Users know their data and know what they're doing, and sometimes that does occur. So what does CE feedback do with these containment models? Basically, we only do these containment adjustments to joins. We don't touch what happens in the histograms or anything like that. We look at the incoming join input estimates and the outgoing estimates. And if there's a mismatch between good and bad, then we might say, I think that the containment model's at fault here. So what we do is, if there's a problem, we just try a different containment model. Let's look at a demonstration of CE containment in action. As you can see, I am running a copy of SQL 2022 and have a 1 GB scale TPCH database set up. First, we'll set up the database further by turning on the right compatibility level and configuring the query store. Next, let's clean the procedure cache to ensure a clean demo. Now we will set up and start an X-event session that will monitor cardinality estimation feedback related X-events as we continue with the demonstration. We can, now that it's started, choose to watch live data. Let's put that in a window off to one side. Before we get started, let's look at the query that we're going to run. We are joining customer to orders on customer key. We've got filters both on the customer table and filters on the orders table. We run this query a number of times. At that point, cardinality estimation feedback might wake up and say, we've run this query enough times that we might consider if there's any feedback that we could try to make the plan better. So let's look at the plan that we did get. And as you can see, the estimates coming out of the join are quite poor. We estimated far more rows than we actually got. But the estimates going into the join are not entirely unreasonable. So let's see what happens when we execute the query another time. Indeed, we see a query feedback analysis event arise. Now, to be clear, we always start with one model of the cardinality estimator that assumes that base containment, that underlying relationship between the two tables. So, however, this hint would basically say, let's try the other containment model, the simple containment model. Assume correlation after the filters. So, we will now run the query another time, and this execution should verify if the query actually got better, the execution got better. So if we look down here, we can see the plans did change, and the CPU time with this model difference has gone substantially down. So it sounds like, or looks like, this CE feedback is good and valid. We can also look at the execution plan and see that our join estimate is more accurate. We get 7 rows, but we estimate no more than 13. So if we run this query a number of times again, we should continue to apply this hint. At this time, we can stop our X event, but we can look to see the hint in the query store query hints table. You can see that we are using this assume a dependence for filter estimates, and that the source of this hint is CE feedback. We can also see this apparent in the query store plan feedback table, which shows that CE feedback provided some feedback that was verified. So at this point, we have demonstrated the change in containment models for cardinality estimation feedback in action. Our next feature is degree of parallelism feedback. In SQL Server 2022, we can identify when parallel inefficiencies occur. So some queries will use too much parallelism, and that would be what we consider a parallelism inefficiency. All that parallelism is actually costing more overhead than if we used a lower degree of parallelism. If we determine that that's going to happen, then we try a lower degree of parallelism, not going any lower than 2, and then we try to see if it helps the query or not. Once the degree of parallelism feedback is verified, so we've run it and we've confirmed that it is actually good for the query, then we could persist it in the query store. It is worth noting that if a user cancels a query that is being verified for degree of parallelism feedback, we interpret that as the query regressed and consider that that degree of parallelism is not good and would go back to a different stable value. We don't recompile any plans. We always revalidate as we adjust up and down, and we never go above any max DOP that you have configured for your server or your query. We only reduce the degree of parallelism and do not go up. As you can see here, I'm using SQL Server 2022, and I have imported the Wide World Importers database. I've created a stored procedure called getStuckItems by supplier and takes as a parameter a supplier ID, which is used in a where clause inside the stored procedure. I've executed this stored procedure with the parameter value 4, and as you can see, the plan creates some parallelism. So we're going to demonstrate how degree of parallelism feedback works with a plan that includes parallelism and works with the query store. So as you can see, the parallelism degree chosen for this query upon first execution is 32. That means that the optimizer may or may not be using too much parallelism for the query to execute efficiently. So let's turn on the feature and use compatibility level 160. Once we've turned on the feature, we can drill down and see how this feature works with the query store to record degree of parallelism, record query performance, and then tweak that degree of parallelism as it goes. So this is a history of degree of parallelism feedback extended events that show the execution of this query over time. On the first execution, we decide that the query is eligible for degree of parallelism feedback. At that point, we decide that maybe we should try a lower degree of parallelism. In this case, we decide that 20 is the right thing to choose. We don't jump down too much because it's like walking up and down a ladder. Just one rung up and down is the right amount. So we execute a few times. We validate that that's good feedback, and so we decide to provide more feedback and try a degree of parallelism of 16. We continue to go down the ladder, continuing to validate the feedback, and then we say, well, how about a degree of parallelism of 12? Again, we validate, and then we go to a point where we decide that maybe this would even work better with a degree of parallelism of 8. At that point, we find that the performance is not as good, and we revert the feedback away from 8 back up to the next rung higher on our ladder, or the last stable degree of parallelism, which was 12. So let's look at overall query execution time in milliseconds in the query store. In this chart, you can see the executions that we have done, and as the degree of parallelism gets lower, the query time is taking less and less time until we reach a fairly stable, fairly performant state relative to where we started. We can do the same by looking at CPU time. And here, we start out with a large amount of CPU time, but as we reduce the degree of parallelism, the CPU time goes down and down until we reach, again, a stable state, much lower than where we started. And finally, memory grant feedback is the third feedback mechanism that we have used. Memory grant feedback is an existing feature. It was first introduced in 2017, and we have expanded its scope. And in SQL 22, we're making memory grant feedback work more efficiently and better for you. The first is persist feedback in the query store. You will see in my demonstration that I will do in a minute that we don't use query store hints, but we do persist it in the query store. And it's the same loop of execute the query, check the query store, do we have feedback? If it works, use it. If it doesn't work, then don't use that feedback and continue to execute. And percentile grant feedback looks at more of the query execution history to determine appropriate grant size. Those are two major changes. Persisting the feedback is fairly straightforward. We put it in the query store, we look it up when we need it. The percentile grant feedback deserves a deeper dive. Without percentile grant feedback, we look at only the single previous execution of a query. So here we have a query that is a parameterized query. And sometimes when we execute that parameterized query, we need a lot of memory. And with some parameters, we need not very much. What can happen when we only look at the single previous memory grant use to provide our feedback is that we can get completely out of phase. What I mean by that, we start with a query that requires 800 megabytes of memory, and that's what we give it. On the next execution, our parameter value, when we execute with a different parameter value, we only need 5 megabytes. But we've granted it 800 because that's what we needed last time. Then we proceed to the third execution, and this time we need 800 megabytes again, but we give it 5 because that's what we needed last time. So by only looking at the single previous execution, you can end up in a pathological scenario of alternating between high and low requirements and being completely out of phase with high and low grants. Memory grant feedback prior to SQL 22 can detect this scenario and self-disable, but what we wanted to do was to introduce percentile grant feedback to avoid the situation. Percentile grant feedback looks at more of the history of the execution. Here's a similar scenario. We start by requiring just a little bit of memory. That's what we give it, and that's what we use. In the second execution, we need more. Memory grant feedback didn't expect this, and so it didn't give very much. On the third execution, we didn't need very much, but both last used grant and percentile grant say, well, last time we needed more, so let's give it more. But as we continue on the fourth, fifth, and sixth executions, you can see how last used grant stays completely out of phase. But percentile grant, by looking at more of the history, can actually zero in on that sort of maximum amount of grant that's needed for the parameters used to execute the query, and hold it steady there so we don't spill to disk. Welcome to the SQL Server 2022 Memory Grant Feedback Percentile Grant Adjustment demonstration. As you can see, I'm using a copy of SQL Server 2022, and I have imported the Wide World Importers DW database, which I have previously enlarged to help the demonstration work. I created a stored procedure that gets dry items by package and takes as a parameter value this pack value, which is used to select in the where clause that package, and we get the total dry items from fact.sale. Before we execute the stored procedure, let's look at what the data looks like under the hood. We can see that the data is substantially skewed. For the each value, we have over 200,000 dry items for that package, but for the bag value, we have only 1,000. So what happens when we execute first with the bag parameter? We can look at the execution plan, and you can see that we actually detected that we gave it too much memory. That is because that is the small value and the average is larger. So we assumed that it would be average, but it wasn't. But when we execute again with each, what you see is even worse. We spill to disk. Spilling to disk is costly and time consuming. So memory grant feedback should kick in and start to adjust. And we need to execute on a repeated basis to learn that the amount of memory that's actually required to execute this query. See, we still continue to spill. We also continue to alternate between the large and small memory grant requirements for the query. And after many executions, we continue to spill. That's okay. The memory grant feedback percentile grant adjustment does learn, but it takes a number of executions. See, we're not getting the warning of excessive grant because we've learned that we want to give it that much memory in order for it to work with each parameter. And we finally reach the point where we are no longer spilling to disk with the large query. So I just want to emphasize that memory grant feedback does not operate through query store hints. Memory grant feedback has kicked in, and we will see that in a minute, but I want to emphasize that it does not show up in the query store hints table. It uses the query store in a different way, and it is stored and visible in the query store plan feedback table. Here you can see that memory grant feedback kicked in to provide additional memory, and that over time it determined that that feedback was valid and should continue to be used for this query. Thank you all. And now I'm going to turn this over to my colleague Derek Wilson, who will be talking about parameter-sensitive plan optimization.
Thanks, Kate. So let's take a look at parameter-sensitive plan optimization. Parameter sensitivity, also known as parameter sniffing, refers to a process whereby SQL Server sniffs the current parameter values during compilation or recompilation and passes it along to the query optimizer so that the sniffed parameter values can be used to generate more efficient query plans. This whole process works out pretty well in most cases, and as my colleague David Pless likes to say, parameter sniffing isn't the problem, it's what it ends up smelling like. That's the problem. Because if we sniff something that is not optimal and end up caching and reusing this non-optimal smell in the form of a bad plan, that is when we run into performance issues. Additionally, What is optimal for the current execution is not necessarily optimal for subsequent executions. Well, David doesn't actually talk like that, but I figured I would try. In any case, this problem can be the most difficult scenario that DBAs run into. When a cache plan for parameters query is not optimal for all possible incoming parameter values, we can see this condition quite a bit, especially when we're dealing with non-uniform data distributions. So, why PSP? We know about parameter sniffing. There's a bunch of ways to try to deal with it. Why even look at something like PSP? Well, PSP is really a way for us to start looking at addressing this problem automatically, right? We'll do so by creating multiple active cache plans for a single parameterized statement. This improvement is only available under dbcompat level 160. However, if you're in a situation where your vendor doesn't support dbcompat 160, you can consider leveraging query store hints to work on your parameter sensitive problems. However, you're missing out on a ton of goodness that gets unlocked in SQL Server 2022 with dbcompat 160. Okay, I think my sales pitch is over. So let me just take just a second or two to talk about this long and confusing sounding title. This PSP and bucketized boundary value selection. I do have as a subtitle, well, actually in parentheses, we're going to use an example of a real estate agent office to kind of make the implementation of PSP a little more easy to grasp graphically. So PSP, how it works is at the end of the day, we're looking at histograms on column level statistics. We use this to identify any non-uniform distributions of data. And that's really where the power of this feature comes from, right? We're looking to optimize for plans that align with different bucketized versions of data distributions that we calculate from the histogram. For PSP eligible plans, the initial compilation produces what we call a dispatcher plan. The dispatcher plan has an element inside of it known as we'll call it a dispatcher expression. This dispatcher expression is used to essentially calculate the cardinality, but at the end of the day, the dispatcher plan's job is to create query variants. The query variants are the entities that do all of the work. These are the things that actually create the query plans that get cached and reused. The dispatcher plan, query plan, not so much. It's really meant to create these query variants. So in this particular example, if we were to say, look at the data distribution within our real estate agent property search by agent table, we can see we have a pretty ginormous table here. We have 3 rows. However, the data distribution between these 3 rows is quite obvious. It's quite significant, right? So agent ID 1 in this case only has 20 listings. Agent ID 2 has about 76,000 listings, and agent ID 3 has over 1 million listings. So PSP would look at this and say, hey, this looks like something I can actually work with. What I will do is I will bucketize my query variants based on this data distribution. So I'll create 3 buckets. I'll create a small bucket, a medium bucket, and a large bucket. Small bucket will consist of, in this case, any agents with less than 10,000 listings, right? And that will help us in this particular example where we're looking for agents where agent ID is 1, that's the value that's passed in. It will help us say, okay, we know there's only 20 listings here. So looking at pulling this data out of this table, it should be pretty straightforward. We should just create a seek, and then unfortunately we have to have a small lookup to get the rest of the columns because our developer decided that they wanted to use the select star. But as such, in this example, since we're doing a seek and a small lookup, we'll probably just need a small memory grant because this should be relatively cheap. And just as a side plug, this feature works 100% and is complementary to the memory grant feedback feature. So if for whatever reason this small memory grant wasn't quite the right size when we first created it, guess what? Memory grant feedback will kick in and save the day. Oh, one other thing I'd like to quickly mention about these the dispatcher plan is this dispatcher plan will be, you can think of recompiled. It will be rebuilt essentially if the data distribution changes. So if we start adding more agents to our agency, or the number of listings changes significantly, we'll generate a new dispatcher plan. And as a new dispatcher plan gets generated, it in turn will generate new query variants. Well, let's kind of talk query variant internals just a little bit, not too much. So I previously explained how query variants are really children of dispatchers, right? And the dispatchers are generated themselves from the original parameterized query. So when the query variant gets created, one way that the PSP feature distinguishes between the different query plans for the query variants is we inject a query hint. This query hint is called plan per value and it has some additional options, which we'll go into in just a little bit. But the reason we do that is that helps us identify the different buckets for each query variant, bucket 1, 2, and 3. And it allows the rest of the SQL Server engine to execute each query variant as its own plan, right? It's just to SQL Server, to the engine, it's just another query with a plan. It's nothing special at that point. But to PSP, it is special. So if we were to look at some quick pseudocode, the dispatcher expression, the thing that is inside of the dispatcher plan, it's doing these calculations, right? So it's looking at the cardinality of the data. Remember our table that had the 3 rows in it? So it's going to say, okay, if the cardinality is less than 100, I'm going to create a query variant with, I'll pass along this select statement, but I'm going to inject this option plan per value and identify that this is query variant 1. Now, again, this is pseudocode, which is why I have the comments here. It will do the same thing for, the second bucket. If the cardinality is less than 10,000, it will create another query variant and say this is going to be query variant ID 2. Otherwise, we'll create a third bucket and we'll say this will be query variant ID 3. So how does the query variant and the query store work together? Great question. So from a query store perspective, we track the parent-child relationship between the original query, the dispatcher, and all of the child query variants. You can actually have more than 3 child query variants, really based on how the data is distributed, how non-uniform things happen to be, right? Having this parent-child relationship really helps us enable the ability to track statistics on query variants associated with an original parameterized query. It's an easier way, at least in the query store, to aggregate statistics instead of aggregating by query hash ID. So all the query variants will aggregate to the same query hash value, even though we do inject that option plan per value. The query hash does show up the same inside of Query Store. You will also see the additional hint, but that is not part of the query hash calculation. The query plans for a query variant from the same dispatcher can be recompiled independently of the dispatcher. Right? So again, they're just like normal plans. They're subject to the normal recompilation rules. And lastly, we did introduce a new DMV, sys.querystore query variant. This really enables us to be able to show, where your query variants are, and to be able to associate those variants with the original parameterized query. This DMV really has 3 columns, has a query variant query ID, which you typically would join to the sys.querystore query table. We have a parent query ID, which typically would get joined to the sys.querystore query table, and then the dispatcher plan ID, which would typically be joined to the sys.querystore plan table. So if we wanted to just logically look at what this would kind of look like inside of the query store, if we go back to our original example, SPX SQL, select star from property search by agent, where agent ID is some parameter. In this case, is a parameter value of 1. This query ID gets stored in the query store. You'll see the original query. You'll also see where the original query creates a dispatcher plan, which also gets a query store ID. There's some additional metadata, the dispatcher expression that gets saved in there. But the dispatcher, as we mentioned before, will go out and generate a query variant. This query variant will have its own query ID in the query store. You'll see the text. You'll see the additional plan that we inject. You'll see the predicate ranges that are part of the bucket. And in turn, this query variant will have its own query plan ID in the query store. Remember, we had this is the small bucket, so this will essentially line up with a seek operation in this simple example. If another value came in, value of 2, we'd have a separate query ID, which would have a different plan shape, but also would have a different plan ID. So let's take a quick look at a demo of PSP. So I've got a CTP build of SQL Server, and we're going to look at the Wide World Importers database. And as a developer, I created a new store procedure that gets stock items by supplier here. Typical query, it takes one parameter, the supplier ID. So based on the data that's been inserted into the stock items table, let's take a look at the behavior of this procedure. I'm going to run this particular store procedure with a sample parameter value of 2. So when we execute this, it should run fairly quickly, and as a matter of fact, we see it results in an index seek. So this is very fast, pretty efficient for this particular query. In fact, if we take a look at the statistics time on output, you can see this runs in about 27 milliseconds, which if it's executed a lot, that's great. Everybody's happy. Now on the right-hand side, though, I'm going to clear the procedure cache, and then I'm going to run the same store procedure, but this time with a value of 4. Now I'm going to run this with a value of 4. As it turns out, there's lots of 4s in this particular data set. So if I look over here, look at the execution plan. Oh, this one is running a scan. What happens if we run the same store procedure again with a value of 2? We just ran with a 4. So the scan is now in the procedure cache. It used to be a seek. Looks like it's pretty fast. And even Management Studio seems to agree with that assessment. But let's take a quick look at the stats output just to validate. We ran in 27 milliseconds the first time. This time it's taking, 294 milliseconds. That's 10 times slower. Now if you're running this query just one time, who cares? But if this is something that runs a lot, well, that's a different story. Let's run this same example in a workload. In perfmon, I'm going to use 2 counters, processor time and batch requests per second. To simulate the workload, I've got a tool called ostress. You've probably seen this in past demos from the team. we're going to use this tool to simulate 25 users running our famous store procedure, but this time with a value of 2. And in the bottom window, we're going to run the same procedure after clearing the procedure cache, of course, but we'll run it with the parameter of 4. So if we run the index seek proc, this one should run fairly quickly. That's not too bad. Let's take a quick look at perfmon. So if we look at perfmon, we see CPU time went up a little bit, but we do have great batch requests per second throughput. This thing is running pretty fast. So if we go back and we run the procedure with the value of 4, the one that does the index scan, this one's going to take a little bit longer because, again, we're scanning a bunch of rows. That wasn't too bad. We'll run the index seek again, and then let's flip back to this perfmon. Wow, look at the purple. We are CPU bound now. Our workload throughput has gone down. It has just tanked. So this is really what's happening in the real world when you see a problem like this. In fact, this is so bad, I'm just going to cancel this thing. Okay, so that's the problem. How do you solve it? First of all, let's look at the data SKU here. This is a count of suppliers. This is the parameter value in this table. As you can see, for the parameter value 2, there's 3 values, and parameter value 4, we have close to 4 million values. You can see the problem here, right? Why one does a seek and one does a scan. In fact, now you see why we have 2 different plans for the possible ranges of values in our procedure. Okay, let's do this. Let's just change the database compat level to 160. That's all that we're going to do. We're not going to change any other code here. And let's go back and see what happens to the workload. So we'll run the seek. The time is pretty reasonable. And if we go down second window, we'll run that scan version of the proc again. And that one runs, okay, it's pretty fast. And we'll just go back and run the seek again. And that should be done here. Yep. So not too bad. And so we'll take a quick look at perfmon. And wow, you can see we got pretty consistent performance here. The CPU got pretty high, but the batch requests per second is identical between these runs. My throughput looks the same. Users don't see the difference. Now, the query store is not required to use this feature, but it does give you additional insight into what's happening. You see I've got 2 plans for the same store procedure. Here's one for the seek. This is the query inside that procedure. And this is the one for the scan. And you can see here I've got the same store procedure query. Now, one of the things the PSP does to make all of this magic work is we have something called a query variant. So the queries show up in the query store from a text point of view. They don't quite look identical. In fact, if you look over here, if we scroll over just a little bit, you can see that there's an additional hint that's been added to the query, this option plan per value hint. This is not a hint that you can run directly, but it does inject into the query via the query variant technology, and we store it in query store this way. The queries do hash to the same statement value, however. We did add additional DMV in the query store that can show when we created these query variants. It has the query variant ID, the dispatcher plan ID, and the parent query ID. These can be used along with some of the other query store DMVs to view additional metrics. Okay, let's take a brief look at the optimize plan forcing feature. As a matter of fact, I'm not going to spend a ton of time talking about the feature. I'd rather just show you the feature because it's so much more impressive than going through slides and this particular flow chart. But the one thing I'll say about this flow chart is really it's intended as a simplified view of the things that we're doing to save time during the optimization process. What this feature's goal is it's really trying to address the problem where you have, say, a query that takes a long time to compile because it's a complex query, and the query the query plan gets kicked out of memory, and so we have to recompile again. The recompile process itself can be somewhat CPU or memory intensive, depending on the complexity of the query, right? So what optimized plan forcing is really intended to do is to speed up the optimization process for queries that have been forced, right? And we do that by capturing what we term a replay script, which is basically we're saving very important optimization rules during the compilation process. We save those rules in a hidden attribute in the showPlan XML. Right? So when the query gets run again, we can look at that replay script and execute the rules that the SQL Server engine would typically do during the normal compilation process. But instead of it having to go through a whole bunch of rules to figure out, okay, should I run this rule against this memo? What we'll do is say, oh, we already have these rules recorded. We'll just replay them directly, which will save time for sure. So the flowchart is really meant to show you, as query gets executed, we check the plan cache. If the plan is in cache, we use it and execute. If the plan is not in cache, we first check to see if that particular statement, this is coming in from the query, is marked as forced, whether that's a manual forcing by DBA or SQL Server forcing the plan because you have the automatic tuning option turned on and we had to fall back to the last good plan. So if the query is marked as forced, we check to say if the replay script is available. If it's not available, we'll say, do we need to recompile for any reason? No. Okay. Let's create the replay script, execute the replay script, and if for whatever reason the replay script was not successful, we will fall back to the query store use plan query hint. If it was successful, we cache the plan and everything is good like it's supposed to be. So enough talking about the feature. Let's kind of show it really quickly. Okay, so I have the worldwide importers database. I'm actually going to set this database to dbcompat 130 because this feature does not require dbcompat 160 to operate. I'm going to clear my query store and the procedure cache. And what I'll do is let's just run this semi-complex query. I'm going to keep track of the stats time output. Okay, so this is running from a cold cache. And have my numbers. We'll just save those really quickly. And looks like I have some old pre-baked numbers. I'm going to just force the query store to flush so I don't have to wait for my 1 minute interval that I've set to kick in. So if you look at the query store, you can see there's my select statement. See how long it took to compile. Only ran it once, so the average and last should be the same. Oh, our feature thought that this query was interesting enough to create a replay script, which is now part of the showPlan XML, which you won't be able to see. Again, it's a hidden attribute. You can see the number of executions. Okay, that's great. So in order to force this plan, you can use the SP query store force plan DMV. You just need to pass in the query ID and the plan ID. And you may notice that there's a third optional parameter for replica ID. So if I had a secondary replica attached to this instance, I could force the plan on that replica. That is not the case here. So I'm going to force the plan. And just so that we do an apples to apples comparison, I'm going to clear my procedure cache. We will run this query one more time. Okay, it is finished. So let's take a quick look at the query store. Let me flush it really quick. I'll take a quick look at the stats from the query store just to do a comparison. And lo and behold, our second run, the average compile duration has reduced quite a bit. It was 338 milliseconds. Now it's only 35 milliseconds from a cold cache, right? And you can see my same options there. So as a replay script, it is forced. Again, this is just a cumulative look at the query store. So hopefully this will impress you enough to say, wow, I really need to start looking at what plans could I really force so that I can get the benefit of optimization replay.
Thank you, Derek. That was a ton of information. So much has improved in the query store and intelligent query processing space. And thank you so much for watching. And of course, thank you to the Data Platform Geeks and the SQL Server Geeks for having us. One last thing real quick. You can win prizes by posting your selfie with the hashtag DPS 2022. Please give session feedback and visit the sponsors. And don't forget to follow the Data Geeks and Data AI Summit on Twitter. And follow me at DPless. Follow Kate, follow Derek for the latest on SQL Server 2022 and intelligent query processing and query store topics. Thank you so much, everyone.